Welcome to UCL AIR's journey in the Student Unmanned Aerial Systems competition. Representing University College London, UCL's Artificial Intelligence and Robotics group are proud to be the first ever UK team to register for this prestigious competition. Meet our dedicated development team, a passionate group of only 7 undergraduate students who've worked tirelessly to bring our innovative UAS to life. Jack Howe is proud to be our team leader, with 1 year of previous UAS experience. Khalid Aga and Arman Abutalebi are the ground control operator and safety pilot respectively. Milan Khatri and Albert Moreno are our software engineers. And Siraj Hirani and Melvin Goy are the hardware engineers. All of us are undergraduate mechanical engineering students, and we will all be attending the competition. That's it, there's only 7 people in our whole development team, but we're not gonna let that stop us from winning. Welcome to the technical design section. This section will give technical details on 10 aspects of our design. For our acceptance criteria, we devised a functions, objectives and constraints table to be used as a guideline to meet the competition requirements. For example, we constrained ourselves to be able to fly at a minimum speed of 50 meters per second, which would allow us to complete the mission within a maximum limit of 25 minutes. A breakdown of our UAV design is shown here. The center of the body houses the cube orange and hair link, which are used to control both manual and autonomous flight. 8 ESCs are housed on the same plate, which transmit power to each of our 8 motors. Our X8 coaxial design uses 2 27 amp-hour batteries to power the motors, which are housed on custom-built arms. A smaller 6.5 amp-hour battery is used to power the auxiliary electronics, such as our LiDAR and GPS. On the underside of the drone, we've mounted our payload delivery system, which uses a winch to safely and accurately lower bottles to the target. Underneath this, we've mounted a Jetson computer and variable zoom camera, which are required for object detection, classification, and localization.
The camera of choice is the CE ZR10 gimbal camera, which is a 4 megapixel gimbal camera capable of a 10 times optical zoom or a 30 times hybrid zoom. The inbuilt gimbal ensures the camera will always look down, regardless of the drone's orientation. The ground sampling distance of the camera from a height of 23 meters was 1.17 centimeters per pixel, with each frame covering 30 meters times 17 meters on the ground. The localization of the airdrop targets was calculated by using a single camera and a GPS module. The longitude and latitude of the targets were determined by calculating the target's location in pixels from the center of the image, and then by using the focal length of our camera, we were able to convert that distance into meters and then into GPS coordinates. The main algorithm used for the color detection is k-means clustering. The largest contour is extracted and pasted onto a pink background. This was done as pink is not a color listed in the regulations and is therefore ignored during the k-means clustering to ensure the background has no influence on the result. The algorithm maps each RGB code of the cluster center to a color dictionary and outputs 2 colors, for the shape and for the alphanumeric. The shape of the targets are classified using YOLO V8, trained on a synthetic dataset of 10,000 images over 50 epochs and by using a batch size of 5. The size of the shapes in the dataset were approximated by using the focal length of the camera. The symbols recognized are then rotated 15 degrees each time before being fed into OCR Tesseract for alphanumeric classification.
For the airdrop task, our team has built a proprietary airdrop mechanism. This uses a DC motor winch that controls a bottle carrier containing 1 bottle. The remaining 4 bottles are stored on an inclined water bottle storage rack controlled by 2 servo doors. When the aircraft reaches the drop location, the bottle carrier is lowered to the ground by the winch via a fishing line and topples once it hits the ground. This causes the water bottle to be deposited on the target. The winch will then bring the carrier back up to its initial position, and the servo doors will initiate to allow 1 more water bottle to be loaded into the carrier. The process is then repeated at the next airdrop coordinate. The system is controlled by an Arduino Uno, and an encoder is installed to monitor the drop progress and control the time taken for each drop. In addition, a capacitive proximity sensor is used for redundancy to ensure that the carrier is in the correct location before the next bottle is released.
For air-ground communications, two telemetry and radio units are utilized. The first of these equipment are the RFD900 radios. RFD900s are high-performance 900 MHz radio modems that facilitate communication between the UAV and the ground control station from distances of up to 40 kilometers. Data transfer is achieved using Mavlink, a lightweight messaging protocol. The throughput of this protocol is well below the 500 kilobit per second air data rate of the radio. Additionally, the radio modems are capable of frequency hopping and signal encryption to ensure reliability and safety. The second communication unit uses the HearLink ecosystem consisting of an air unit and a controller. The HearLink air unit has an RC receiver to allow manual flight using the controller. At the same time, the air unit communicates with the controller using Mavlink. Hence, the controller can act as a secondary ground control station. HearLink uses a 2.4 GHz frequency band and has a range of up to 20 kilometers. The combination of these two telemetry systems allow for reliable communication even if one of the systems fail.
The team would make a coaxial quadcopter which is driven by 8 motors, each providing a thrust of 6.7 kilos. These are powered by 2 lithium-ion batteries which give the UAV a flight time of 27 minutes at full speed. The chassis was designed around these components with compactness in mind to minimize aerodynamic resistance. The chassis was manufactured through 3 main processes: CNC milling, laser cutting, and 3D printing. These methods were chosen as they would reduce manufacturing lead times, allowing more time for testing and implementing design developments. The final airframe has a span of 1.15 meters, a takeoff mass of 15.5 kilograms, and prop size of 28 inches. It also has an expected cruise speed of 44 miles per hour, giving it an expected range of almost 17 miles.
To achieve autonomous flight mission in the competition successfully, our navigation system is handled by the Pixhawk Cube Orange, which runs the ArduPilot autopilot firmware. Through the use of MavROS, which is a Mavlink extendable communication node for ROS, the navigation system can be controlled by the onboard computer entirely. Mission Planner is used as the ground control station to monitor the state of the autopilot and visualize the position of the UAV. Before the start of the mission, the predefined waypoint in the paper format is detected and uploaded to the waypoint database using alphanumeric algorithms. Once this process is completed, the UAV awaits for an arming and mode change command, after which it will initiate the entire mission automatically, which includes navigating the competition waypoints, begin the obstacle avoidance algorithm if obstacles are detected, and also execute the coverage and airdrop sequence in the drop zone area. For obstacle avoidance, a 2D LiDAR with a 360-degree horizontal FOV is used. Point cloud data of any objects within 100 meters range are collected and then segmented to identify the number of obstacles and its distances to our UAV. Next, since the obstacles will be dynamic, we are introducing a novel concept to predict the future trajectories of the obstacles using Kalman filter. The present and the future predicted locations of the obstacles are then fed into the path planning algorithm, which is the artificial potential field algorithm. Our system updates the flight plan by generating local waypoints that the UAV can follow so that it can fly to its next global waypoints without coming into contact with the current and the future positions of the obstacles.
There were many instances where we considered several alternatives. For instance, we used a quantitative approach to determine what airframe configuration was best suited for the competition, whether that was a quadcopter, hexacopter, octacopter, etc. Also, for the airdrop mechanism, we considered using a parachute, a winch with electromagnet release, or even a bungee jump concept. Again, after a quantitative approach, we decided to use the following design. Lastly, we researched several camera and gimbal possibilities. We tested the GoPro 11 with a Tarot gimbal. However, we concluded that the ZR10 would be the perfect combination of lightweight, resolution, and connectivity. The team developed a risk management plan and conducted a thorough risk assessment to identify and mitigate any potential risks. We looked into operational, technical, and also financial risks. The full risk assessment is shown here, as well as a test plan. One of the biggest risks is mechanical failure, so we're taking extra precautions like double checking nylock, Loctite, and fasteners with experienced technicians before every takeoff. Another risk is a loss of communication with the drone. To mitigate this, we're using a backup redundancy communication channel. Software in the loop with Gazebo software was also used to test navigation and object detection and classification code before deployment in the UAV. This reduced the risk of faulty code. Lastly, proper documentation of UAV regulations, both in the UK and the US, were completed before maiden flight.
Now we'll move on to the flight readiness review. This section will provide key metrics on 7 different areas of our aircraft's performance.
The performance of the imaging algorithms have been improving throughout each iteration. After 52 airdrop tests, the mean error of the localization of the target was 3.5 feet. The accuracy of the shape classification was 92%. The accuracy of the character classification was 82%, and the color accuracy was 93%. This is an example of character classification processing and the corresponding confidence levels. This confusion matrix shows the performance of the color algorithm, in which it showcases an overall accuracy of 93%.
To ensure that the airdrop system worked well, a total of 6 sets of airdrop tests were conducted and all of them were considered successful. For each set of tests, 5 water bottles are dropped from a height of 75 feet and they are dropped one at a time. The result shows that maximum drop accuracy was 0.6 feet away from the target and 90th percentile distance from target was around 0.54 feet.
To test the performance of our telemetry equipment, we designed a mission to fly the UAV 1.5 miles away from the ground control station and the RC controller. The mission log files demonstrated that during the mission, around 23,000 packets were received by each of the ground control station and the controller, while 1,500 packets were transmitted back to the drone. During the entirety of the mission's 4 minutes, there were 0 failed packets. This indicates the robustness of our communication system.
To test the aircraft's performance, 30 flight tests were conducted. These were a combination of both manual and autonomous flights and totaled 4.8 hours of total flight. We also conducted 5 additional tests in which the UAV took off and landed immediately. This was done to ensure that the UAV would be able to withstand the loads experienced during these extreme phases. Through testing, the average flight range was found to be 14.2 miles and the top speed was 45 miles an hour. We were also able to ensure that the UAV met all other flight performance requirements.
Our UAV conducted 25 autonomous flights in which it attempted 249 waypoints. With 100% success rate, it reached 249 waypoints with the average waypoint miss error of 1.48 feet and a maximum waypoint miss error of 2.62 feet. This demonstrates that our UAV can reliably navigate through waypoints within the competition requirements of 25 feet. In terms of obstacle avoidance, we tested its performance by flying our UAV autonomously during its waypoint navigation with other UAVs in the same airfield controlled manually. For static obstacles, we can reliably avoid 20 out of 20. For dynamic obstacles, we performed 10 tests. Each test consists of 1 dynamic obstacle. We successfully avoided 6 obstacles without any human intervention for manual override. UCL AIR has conducted 5 full mission tests to validate the performance of each subsystem when integrated together. For the timeline section, we can comfortably execute the setup, mission, and teardown within the time restriction, hence we have scored an average of 100%. For operator, our UAV platform was designed from the beginning with the intention to achieve high autonomy. Hence in the mission test, we only require 1 GCS operator and 1 safety pilot. We successfully delivered an average of 3.2 bottles according to the competition requirement across all 5 full mission tests. This gives us an average score of 64%. Throughout all full mission tests, the team was put under competition setting to mimic the pressure that would exert on us in real life. We have resolved any certain problems with high professionalism and succinct communication that has ensured the full mission test to be carried out in a safe manner. We therefore has evaluated our operational excellence score to be 100%. The average full mission test score for all 5 tests was 82%. With more practices and familiarities, we predict an upward trend of our full mission score with high confidence.
With just 7 passionate and determined students, 6 months of tireless work, and a tight budget, UCL AIR has created a drone that boasts advanced flight capabilities, intelligent obstacle avoidance, robust imaging, and pinpoint accurate payload delivery. As a first-time competitor, we're bursting with pride to showcase our technology at this prestigious competition. Get ready to watch UCL AIR soar to new heights on the global stage. Welcome to the appendix of our video, which includes the mandatory proof of safe flight section. The first clip is of a manual flight, where the drone gets 1,000 feet away from the safety pilot. The pilot performs a manual takeoff and then heads the aircraft out into the field. At this point, the aircraft has reached a distance of more than 1,000 feet away. Now it's time to turn the drone around and bring it back. The safety pilot carefully navigates the aircraft back to its starting location. The landing process then commences with the aircraft's altitude decreasing. The safety pilot then maneuvers the aircraft just slightly closer before finally landing. And that's it. The aircraft is now gently and safely landed. Now onto the autonomous flight with a transition to manual. First, the aircraft is taken off the ground manually, and then a quick switch to autonomous commences. The aircraft autonomously navigates to a waypoint over 200 feet away, at which point there is a transition to manual. From here, the safety pilot takes over and brings the aircraft back to the takeoff point. The aircraft is then lowered, before being reoriented and brought slightly closer to the safety pilot. After that, the safety pilot safely and gently lands the aircraft. This final section shows that our aircraft can perform within the minimum requirements of the competition. The aircraft takes off before navigating through a series of waypoints. It then performs a loop of the course. Each loop is 1.3 kilometers, or about 0.81 miles. It does 15 loops of this course, which comes out to a total of just over 12 miles. Since the drone is a coaxial quadcopter, it takes off vertically and has a turn radius that is significantly lower than the minimum requirement of the competition. Throughout this entire course, the aircraft remains above the 75-foot AGL requirement. Once the aircraft has completed its 15 laps, it comes back to base and performs a safe landing. Thank you once again for your attention to our video. We look forward to seeing you at the competition this June.